Hi, this is Curtis Whitson. Welcome to the second part of this half-day course on advanced black oil PVT. We'll just go ahead and get started. The topics that I'll look at are what is a black oil PVT model? How do we create black oil PVT models? How do we use black oil PVT models? And finally, some special challenges in black oil PVT models. So we'll get started with what is a black oil PVT model, and basically it's a PVT model that provides both phase and volumetric behavior of a fluid or fluid phases, for example, gas and oil or single phase, at any pressure and temperature. It's using a two-component description, G hat and oil hat, as we'll use throughout this presentation, which basically represent the pseudocomponents, surface gas and surface oil. And the 6 different PVT properties in a black oil model are all pressure dependent, 3 for each of the 2 phases, gas and oil. Now, if we look at the first black oil PVT property, the solution surface volume ratio. For the oil phase, it's the familiar capital RS, or solution gas oil ratio. And for the reservoir gas phase, it's the solution oil gas ratio, or CGR, solution CGR, that's a little less commonly understood and used. The second property is a volume factor, sometimes called formation volume factor, but in our case, we're going to look at black oil PVT properties that can be used, for example, in calculating pipe flow and pressure drops. And there we'd be talking about tubing volume factors, but the volume factor is represented by symbol capital B for the oil phase, BO, and for the gas phase, BG. Very familiar quantities to petroleum engineers. And then finally, we've got the phase viscosities, mu O and mu G. These are the 6 pressure-dependent properties. Now, for every black oil PVT table, it will be representing a single temperature, which is fixed or constant. So if you have a black oil table, it'll be useful only for one temperature. So if you're going to do black oil calculations of pressure drop in tubing, for example, where the reservoir temperature at the bottom goes to the surface temperature, it could be, you might need 4 or 5 different tables for the different temperatures up the wellbore. The 6 pressure-dependent properties, capital RS, little rs, BO, and BG, and mu O, mu G. Now, in addition, there's, for the last 4, BO, BG, and mu O, mu G, those properties will be specified as saturated properties or undersaturated properties. And these are very important to differentiate, and we'll come back to how that's identified and defined in the black oil formulation. The other thing is that the 2 surface products, surface gas and surface oil, have properties, namely density, that are required to use a black oil PVT model, rho O hat and rho O G hat. These surface pseudocomponent properties are assumed to be constant, not dependent on pressure, whereas in reality, we'll find that those surface products that are created from oils and gases at different pressures and different compositions will actually vary with pressure, but in fact, we ignore that variation. So in order to use a black oil property, we need to have some kind of a surface process that will translate a phase in the reservoir, phase in the tubing, gas phase or oil phase, whatever it might be, into through a surface process, and that will create 2 products, surface gas and surface oil. And those 2 surface products define our 2 pseudocomponents. So the black oil properties, BO, BG, RS, little rs, those 4 properties will be dependent on what process you choose to use at the surface. This is just a schematic showing a generic fluid entering a surface process, which is shown here with the dashed line. Basically, it's a three-stage, in this case, a three-stage multi-stage separator process, where the gas from each stage is removed and collected together to provide the total surface gas, and we end up with the final surface oil product. So we've got these two products being generated from an incoming fluid, and that fluid might be a single-phase gas or a single-phase oil, and it would be specified at a particular pressure and temperature. Just remember that for the Blackwell table we're creating, it'll be at a fixed temperature. Now we'll know the volume of that phase at the pressure and temperature. So this is a generic kind of structure of how the Blackwell PVT properties are going to be calculated and how they're going to be defined. So let's look specifically first at the gas, if we have a gas phase here coming in. So let's just take a look at this. I'll write this in red. So if we've got a gas phase coming into the process, we'll have composition YI. We're at some, of course, the temperature of the Blackwell table and some pressure. And because it's a gas phase only, that will be at a pressure greater than or equal to the dew point of that gas. And we'll know the volume of that. For example, for a 1 mole amount, for example, if we just use a basis of 1 mole entering this process, then we'll know the volume of this gas at the pressure and temperature. Okay. Now, because the pressure is greater than or equal to the dew point, this 1 mole, for example, of material that we're putting into the process, the amount of products, the volume of surface gas and the volume of surface oil over here will be independent of what pressure you're at coming into the process. Okay, basically you'll flash it down to two phases, the first stage and so forth. So the volumes of products are independent of this pressure here, but the volume of the phase itself is clearly a function of the pressure through its compressibility. So in this case, we're going to say that we get this surface gas product, and because we're going to get something similar from an oil phase, we need some nomenclature that will identify where the surface gas product is coming from. So we're going to add another G behind that to say that this surface gas product is coming from a gas phase at P and T. Likewise, the surface oil product is coming from a gas phase, and this is typically, instead of surface oil, called surface condensate, since it's coming from a gas. It's surface oil, which is usually referred to as a surface condensate, stock tank condensate. So these are the three volumes that will be used in defining the Blackwell PVT properties. Now, in addition to knowing the volume here of this gas phase at P and T, we will also know its viscosity through some model or measurement. That's the third PVT property. This property is independent of the surface process. Now, the formation volume factor of gas, which is the one, actually, let's start with the volume, the solution volume ratio. The volume ratio little rs for the gas phase is defined as the amount of surface oil or condensate coming from the gas phase divided by the surface gas product coming from the gas phase. That's our so-called CGR solution oil gas ratio. So that's by definition our little rs term. The BG term, and for Blackwell tables, we're going to define it as BGD, and we'll come back to this in more detail. This is defined as what gas volume you start with, the phase as a single phase at some pressure temperature of the table, and so any pressure that's greater than or equal to the dew point. Okay, and that will be divided by the surface gas product that you get out from that gas phase. And this surface gas product volume is independent, as mentioned earlier, independent of the pressure. So these are the two properties for the gas phase, and they have these symbols. If we go to the oil phase, I'll switch colors. Green. So this is our oil phase with composition Xi. This is at some temperature for the table and any pressure greater than or equal to the bubble point pressure of that oil at this temperature. And again, we'll know, let's say that we assume just as an arbitrary basis that we've got 1 mole of material of this oil. We'll know its volume from either measurement or calculation, volume of oil at the pressure and temperature. And we'll know its viscosity, which will be dependent on pressure and temperature is fixed. Now the viscosity again is not dependent on the surface process, neither is the oil volume. But the product volume that comes out of flashing this through some process is the surface gas product, and we'll use the nomenclature GO here, surface gas product coming from an oil phase, and surface oil product coming from an oil phase. So these will be the nomenclature we use here. So now the properties for the Blackwell PVT properties for the oil phase, which are dependent on the process, RS, solution gas oil ratio, can be defined as the surface gas product coming from the oil phase over the surface oil product coming from the oil phase. And likewise, the oil formation volume factor, the oil volume factor, is just defined as the oil volume, which is at the temperature of the table and any pressure greater than or equal to the bubble point. That will vary with the pressure, but the product volume, surface oil coming from that oil, will not vary with pressure. So that's the RS and the BO definitions. So again, surface process is having an effect on the solution volume ratio, capital RS or little rs, and the volume factor, BO and BG. The viscosities, μg and μo, are independent of the surface process, but they are dependent, of course, on the pressure, mainly through their dependency on density of the phase. So let's start talking about the surface volume ratios. We've already gone through these definitions. Now, the SBE nomenclature for capital R is gas-oil ratio, and little r is oil-gas ratio. But you have to be careful because in this case, for the solution gas-oil ratio, it's not equal to 1 over the solution oil-gas ratio. And that's because the RS is describing the surface volume ratio for the oil phase, and the little rs is defining the surface volume ratio for a gas phase. So it's not the same material we're talking about, so you don't expect them to be equal. Now, they will be equal at one particular pressure, at a critical point, but otherwise they're not equal. These quantities are really the Blackwell equivalent to composition. So the RS term is really giving us an indication of what is the oil composition. What's the mole fraction of the oil phase that's surface gas, and what's the mole fraction of the oil phase that's surface oil. Likewise, the little rs term is giving an indication of what is the molar composition of the gas phase. Now, we may use I being the two pseudo components, or in fact, you might even consider I as being the actual true components, nitrogen, CO2, methane, and so forth. So these are this translation from the solution volume ratios to composition is something we'll come back to. So let's look first at the oil phase solution GOR, RS, here. And the pressure dependence of that will be as follows. Basically, you'll have it, usually it's monotonically increasing. It doesn't have to be. And for gas condensates, you'll often find that it is not monotonic, that it increases from low pressures and then it reaches a maximum and then drops back down. But in this case, we're looking at a normal oil solution GOR behavior that's monotonically decreasing from the initial bubble point. For example, if you start with an oil, and basically the oil shrinking continuously as we drop the pressure here. If we have a low GOR oil, let's say less than 500 cubic feet per barrel, 100 standard cubic meters per standard cubic meter, this will be more or less linear, where this goes from more or less the intercept 0, 0. Actually, it'll be close to that at least, and more or less linear. If you have a high GOR, let's say above 1,500 cubic feet per barrel, 300 cubic meters per cubic meter, and up to a near critical, which might be as much as 3,500 standard cubic feet per barrel or 600 cubic meters per cubic meter, then the RS curve is going to look like an S, kind of a very nonlinear curved with changing shape, and it'll be almost asymptotic if it's a critical mixture to this point here. Now, normally the path is that if we start with an oil, and maybe it's undersaturated out here, the reservoir is depleted, you drop below the bubble point, maybe in the reservoir, reaches some pressure here. At that point, you decide to do water flooding as an example. Then you might be moving in pressure upwards again, and the properties of the oil will have changed. It'll have less gas in solution. Its composition will have become less gas rich, less methane rich. Its density will be higher, its viscosity will be higher, and so forth. And then as we move up into higher pressures here, the properties of BO and viscosity will again change. And it'll change differently for this oil than it did for the original oil, because this original oil had more gas in solution, was more volatile. And as you drop down here on this curve here, if you did the water flooding from this point, this is basically a low GOR oil with very little volatility. So this would change the properties of BO and viscosity would change differently with pressure here than it would for the original oil. This is just an example of a volatile, basically a volatile oil. We can see it's got a solution GOR here about 2,300 standard cubic feet per stock tank barrel. So that's a volatile oil. It's got a bubble point about 6,500 psi, just as an example. Now, above this particular oil, this oil here, above the bubble point pressure, of course, its composition does not change. But if we looked at this situation here where we go below the bubble point, gas comes out of solution, and then if we recharge the pressure of that oil, you'll be coming up with a different composition. So there's actually a series of these curves if you look at a reservoir process, for example. Now the oil phase volume factor, we again sometimes call it formation volume factor when we're using it for reservoir conditions, is defined. This was the generic definition of the volume factor, is that it's the volume of the phase at pressure and temperature, and this is at a pressure above the saturation pressure of that phase, divided by the volume of the product. So if it's an oil phase, it'll be the oil, surface oil product, shown here. So it's the oil phase and the surface oil product coming from the reservoir oil. We often use the inverse of formation volume factor as little b, as is the SP nomenclature. So here you just flip it upside down, and this is related to shrinkage, which I'll come back and talk about here in a minute. Now the oil volume factor range will typically go anywhere from 1.0x for like going from a first stage separator to stock tank, it might be 1.07. Even a low GOR oil, 200 cubic feet per barrel. In some parts of the world, you'll find these low GOR oils will have some initial oil formation volume factor less than 1.1. But typically, it'll start around 1.2 for most oils being discovered today. And you might reach as high a value as 3 to 4 before it flips while it's still a bubble point. But typically, most oils today are probably 2 to 2.5 at the most. That's the range of the properties initially. Okay, Now, the shape of the volume, formation volume factor. So if we start at the bubble point here, okay, if we go to higher pressures, we're basically just, the oil is being compressed. So this is a compressibility effect. You got more compressibility near the bubble point than far away from the bubble point. So the slope of this line is a little bit steeper here near the bubble point than further away. So that's why we're seeing the change in the oil volume with pressure. But when we go below the bubble point, the change in oil volume is more abrupt, and it's caused mainly, well, exclusively, the reduction in volume is coming directly from the fact that gas is coming out of solution. It's losing mass. So the oil is shrinking because gas is coming out of solution. As more and more gas comes out of solution, the oil volume shrinks down towards approximately 1, if you forget the temperature effect down below. So basically, the shrinkage of the oil below the bubble point is shown here. The compression of the oil, or if you're starting out here at initial pressure, the expansion of the oil here, constant composition, until you reach the bubble point, and then the oil volume will shrink, in this case dramatically because it's a volatile oil. Now, this is an example showing both the saturated, the previous curve is the saturated, these are the saturated formation volume factor behavior, and the undersaturated. But actually, every oil, as this oil loses some gas and goes down to this oil will have its own undersaturated set of properties. You see, it'll be a little bit less steep, the change in the oil volume. The compressibility is decreasing when you lose gas, and when you lose a lot of gas, you get a very flat curve here, which means the oil compressibility over this pressure range. If you just look between 10 and 12,000 psi, the compressibility is much lower here than it was up here, mainly because you've lost these light components out of solution. So these are the undersaturated BO properties, and along this line here are the saturated BO properties. Okay. Now, one interesting thing is that you've got this very nonlinear behavior for, basically these very volatile near-critical oils. But the interesting thing is that the shape of the BO and the shape of the RS as a function of pressure here, I lost my axis label there. The shape of the BO and the shape of the RS are very, very similar. And because they're similar, what you'll end up with is that if you plot saturated BO versus RS, you'll get a very linear trend, approximately intercepting the 1. It'll be a little bit greater than 1 because of temperature effect, but a very straight line for all of the saturated, no matter how nonlinear the BO and the RS might be. They might both look like this, but when plotted against each other, the plot is a straight line, more or less unit straight line. Now, the last comment about the oil volume factor is that often we talk about the shrinkage factor. And basically, the shrinkage factor is saying that if you start with 100 barrels at pressure and temperature, okay, and you bring that to the surface and you only have 50 barrels left when you get at the end of the surface process, then you would basically be going from 100 barrels at reservoir conditions to 200 barrels you'd start, this is actually here, this is the inverse here. So you start with 200 barrels in the reservoir at P&T, and you end up with 100 barrels here at the surface. And that shrinkage factor would then be 50%. You're going from 100 to 50 barrels. So the equation for the shrinkage factor is basically 100% times 1 minus the little BO. So you can see here for a 1.1 BO, you basically get a 10% shrinkage. When it comes to oil viscosity, these curves are going to look very much like the inverse of the BO curve. Okay, if you actually flip this upside down, it would look very much like the BO curve, but a little bit exaggerated. And the reason for that is that the oil viscosity is very closely approximated by, in fact, if you take the log of the oil viscosity, by oil density to a power typically around 3 to 4. And what that means is that, well, oil density is basically inversely proportional with BO. Okay? Which means that that would basically be 1 over BO to the 4th power, or BO to the 4th power. So these are going to be a little bit exaggerated. So if you look at this is the saturated oil viscosity. It's increasing dramatically because of the gas coming out of a solution. Consider the solution gas like a lubricant. You're losing the lubricant from the oil, and you're going to get a more and more viscous oil. The viscosity change for the undersaturated region of pressure for the initial oil is going to increase, but that's simply because the density is increasing as the pressure increases. Now we're going to put all of the undersaturated properties and saturated viscosities together. So we've got along this line here, these are the saturated viscosities. And then for any new oil, this oil has more gas in solution than this oil. And of course, the original oil is somewhere out here, maybe this one here. So you basically have, what you see here is that you get, for the oil with the most gas in solution, there's much less viscosity increase with pressure. And likewise, and that's because the pressure, the density change due to compressibility is smaller than the density change due to losing all of this gas from solution. And when you get less gas in solution, you get a higher compressibility and you get a higher density change. So you basically see that this oil viscosity is changing. And you can check and see how well that relationship between viscosity and density is by taking your entire Blackwell data set. In this case, we're plotting the oil viscosity on a log scale and the oil density to the power of 4 on the x-axis, and you see that you get a pretty linear trend for all of these data that we just looked at here. So they all collapse into a pretty close linear trend. So now we're going to talk about the gas phase Blackwell PVT properties, and just remember that's the solution oil gas ratio, or solution CGR, the formation or volume factor, and we wrote it as BGD, and the gas viscosity. So we're going to talk about these three, and just the general shapes of these, just to get you, this is not as familiar to people. So basically, if we have the initial dew point, for example, here, that could be the actual reservoir gas, or it could be the incipient gas from the bubble point of an oil. And that's going to drop down. This is a little RS. It's going to drop down, usually rather dramatically, flatten out a little bit. And then, of course, in the relevant ranges of pressure that you're normally seeing in the reservoir, it's basically monotonically decreasing. But if you go to low enough pressures, you'll actually, those heavier components will start liking to be in the gas phase again, and this will actually turn around. And if you go to low enough pressures, this thing will really crank up and kind of go asymptotically. Those components at low enough pressures really like to be back in the gas phase. But for practical purposes, this range of pressure is not too interesting here. So we've got a solution oil gas ratio that will look something like this. Formation volume factor, we plot that versus pressure, BG, because it's inversely proportional to pressure, will look like this. Be something monotonically looking like that. Okay, a little bit hard to read. And what we normally do is that we plot instead the inverse of this, which is proportional with pressure, and then we get something that's quite linear, maybe a little bit of turning there, and we're able to read on a linear scale all the values of this. And this is called the expansion factor, just the inverse of the BG. And then because gas viscosity is approximately linearly changing with density, gas density, we basically get something that looks something like this, that we got fairly flat here. And something like that. So the range here might be 0.1-ish centipoise from about 0.01 down here. So it might be a log scale looking something like this. Gas viscosities can reach and even exceed 0.1 centipoise, but normally they're less than 0.05 centipoise. So this is what the three properties look like as a function of pressure only. That's not really taking into account the. Now, what we clearly see here is that there may be significant composition changes of the gas, right? Remember, gas composition is directly related to solution GOR, so solution OGR. So you may have some composition dependence that you're not really seeing in these figures here. Let's look at a real system. This is the volatile oil again. It has initially 190 stock tank barrels per million standard cubic feet. That's a very rich condensate at initial dew point of about 6,400 pounds. It drops down to about 30 stock tank barrels per million standard cubic feet. So that's basically, and again, if we would have continued this calculation to even lower pressures, then this would have come up here like this. Okay, so let's see, make a couple of comments about this. This is starting up here. The initial will typically, this is for a lean gas condensate, might start at 20, 30 barrels per million, or a rich gas condensate, near critical, might reach 400 barrels per million, still being a dew point. The minimum down here will typically go from 5. If we start at 20, it might go down to 5. If we start at 300, it might go down to 20, something like that. We typically don't get down to this low pressure range, so this expected revaporization, according to this curve, probably will have minimal effect on condensate recovery for various reasons. If we look at the revenue coming from a gas condensate, just a gas condensate development, and say that we start with a rich gas condensate at 300 barrels per million, probably as much as 80% of the revenues are coming from the condensate, the surface oil, and only 20% from the surface gas. And that'll be the case all the way from the initial pressure down until we could drop below the dew point. But as soon as we drop below the dew point, as the average reservoir pressure drops down and the amount of condensate carried with the gas decreases, the amount of revenue coming from the condensate decreases from 80 to 50%, and down here it might be as little as 15% or less. So that's an important, this is a very important PVT property because of the bottom line effect on economics. Now the gas phase volume factor, or gas phase formation volume factor that we're most used to looking at, is just defined as the gas volume at pressure and temperature divided by what that gas will yield after going through a process as a surface gas product. And we often use the inverse because of it being approximately proportional with pressure. So this is called the expansion factor, and typically for most gases above initial pressure of 1500 psi, which is the vast majority of gas reservoirs, the expansion factor might range from 100 to 250, maybe reaching as much as 350 for really rich gas condensates at high pressures. So that's the expansion factor. So if you take out 1 cubic meter of reservoir gas, you get 100 standard cubic meters of surface gas for a low pressure system, or maybe a factor of 3 higher than that for a higher pressure system. Now, most textbooks in petroleum engineering will make the assumption that all reservoir gas ends up being surface gas and there is no condensate. That's just because historically there was not so much condensate or being brought to the surface that it had a big impact on the economics. So they basically assumed that the solution oil gas ratio was approximately 0. They neglected it. And as a consequence, if you make this assumption that all of the surface gas is the reservoir gas, then from the real gas law and the ideal gas law put together, then you get this classic equation for gas formation volume factor. It's this constant here times the temperature of interest, the Z factor, which is a function of pressure, temperature, also gas composition, of course, divided by pressure. So this is the classical equation of gas formation volume factor. Now, this is not really what we're going to be using for the vast majority of reservoirs today, because the vast majority of reservoirs today, any gas that comes out of the reservoir will usually carry with it enough condensate in solution that it should not be neglected or ignored. So, yeah, we've already looked at this pressure dependence of the formation volume factor. I'll re-sketch it here. BG kind of looks like this. That's BG. And 1 over BG is more or less linear, maybe turning something like this. But this is the expected behavior for a constant composition of gas. What we're going to find is that because the gas composition is changing as condensate drops out in the reservoir, the gas in the reservoir becomes leaner, you're going to get a different shape than that. So now let's take a look at what we're going to refer to as dry gas and wet gas. Okay? Now, it's a little bit confusing, and I'm going to try to sketch this out, but basically we're going to look at two ways of treating the same gas. This is a gas phase. Okay. And in the one case, we're going to actually put it through an actual multi-stage process. And we're going to come out with a surface gas product and a non-zero money-making condensate surface oil product. And this gas here, we're going to use and label as dry gas. Now, what do we mean? We're not talking about the dry being down here. We're talking about, is it a surface dry gas? Well, it's dry. It's been dried. Why we call it dry is because we've removed surface condensate. Right? We've removed that into its own product here. So this is true surface. That surface gas is dried. Been dried, liquids have been knocked out through the separation process. Now, sometimes we want to look at that gas phase brought to the surface. Okay, brought to the surface. And for some crazy reason, what we want to say here is that coming out at the surface is only surface gas, and that you get no surface oil. But that's not really what we're saying. What we're going to actually do here is that we're going to raise this. It's not really zero, but what we're going to do is the following. We're going to say that that surface condensate that comes out of the oil, we're going to convert this to a fake surface gas. Why would you do that? It's another discussion. But we do that in engineering of gas condensate fields. We sometimes want to do that. And what we're going to do is that we're going to take that, and the way you convert that is that you have to convert first this volume of what's actually a liquid, you multiply by its density of that condensate, and divide by the molecular weight of the condensate, okay? And what that does is that turns that into the moles of the well stream that was processed, the gas well stream that was processed. It converts this surface condensate into a molar quantity. And then we use that molar quantity and multiply that by the conversion from moles to standard cubic feet of gas. Well, the conversion from the ideal gas law of any number of moles. This is from the ideal gas law. If you just say you've got some moles of something and it's going to be created or considered as an ideal gas, then this will be, this term here will be R standard temperature over standard pressure. That's the equation. And if you're using field units, that's about 379 standard cubic feet per pound mole. If you're using metric, it's about 23.6 standard cubic meters per kilogram mole. Okay? So we're just going to multiply it by this constant, whichever you want to use, to get your standard, your fake equivalent standard condition gas volume. So what we're going to do is that we're going to add that together. We're going to add these two together. Okay. Into what we're going to call a wet gas volume, which is the true dry gas volume at the surface, plus this converted times this, well, it's first got to be multiplied by this term and then by this term, okay? And we'll just call this a gas equivalent term. Actually, I think we usually use it as COG in the text, in the monograph book, we use the term COG. Pretty sure it's COG. Conversion from O to G, from a surface oil to a surface gas. And so that wet gas concept, this is what we're going to call wet gas. It's a surface wet gas. Okay? That, like that. Now, what we want to use in our engineering calculation, reservoir simulation, some material balances, certainly pipe flow calculations, is this so-called dry gas formation volume factor, where we're actually using this term here. Well, what you can show is that the equation for this is exactly this term here, which is our traditional gas volume factor. But we're going to call that BGW because this assumes all the moles from the reservoir gas end up being surface gas, or the fake gas. Okay, so we're going to call this BGW, what we calculate from the traditional equation out of the textbooks. But then that needs to be corrected for this amount of moles that actually turns into a condensate. So how do you get that? Well, there's equations to do this conversion to come up with this number. You can find them in different books, the monograph, the phase behavior monograph, for example. But if you just want to know an estimate of how big of a change this is, it'll always range somewhere between 0.01, maybe as much as 0.2 for some gas, really rich gas condensates. It might be a 15-20% correction, or it might be just a 2% correction. So where do we get this order of magnitude for what is the correction? Well, you can just go and look at what is the composition of my gas. And if you just look at the mole fraction the mole fraction that's either C5 plus or C6 plus, don't really care. So for example, if you've got a gas with Y of C5 plus equal to 0.08, that is going to be rule of thumb very close to what this number here should be. So basically this C5 plus is going to be representing your condensate and the C4 minus your surface gas as an approximation. So it's going to be a correction of somewhere around 8%, 1 minus 0.08. So this term will be 0.92, and then 1 over 0.92 is about 1.08. So it's going to be about an 8% correction. This BGD is going to be 8% higher than the traditional BG definition. So this is something that you can't ignore when the correction terms are in the magnitude up to 15 to 20%. Now we're going to just look briefly at this is the inverse gas formation volume factor. And for this volatile oil, so the original, this is volatile oil, but the incipient gas of that volatile oil that had 190 barrels per million, little rs, its BG is equal to this at the original dew point pressure. As you lowered the pressure, you had less condensate in solution. And actually, that change in composition, you're dropping the pressure, so you'd normally expect the little BG to drop. But instead, the little BG increases as you go below the dew point because the gas composition is changing so much, it overcompensates for the pressure reduction, and you actually get an increase in the little BG for a couple of pressures before it starts going down. If you take the incipient, that initial dew point gas, and you go to higher pressures, then all you're seeing is compressibility factor. And you got this basically little BG behavior here of the undersaturated initial dew point gas. But if you deplete the gas down here, and then you go to higher pressures, maybe by water influx or water injection or something, and then you go up in pressure, its undersaturated curve is going to look quite different than the original little BG expansion factor. So what you see is that this change here is mainly due to the change in the composition with pressure below the dew point, or the changing RS, little rs with pressure. So it's a big composition effect on the little BG. So these are your undersaturated properties, along with the points along the line here are the saturated properties. Now, because viscosity is strongly tied to gas density, we get exactly, because this is basically proportional with little BG. So you get a very similar shape here effect and on the gas viscosity. And you see here for this very rich condensate at a very high, this is the original 200 barrel per million at 12,000 psi. It's just slightly below 0.1 centipoise, which is about as high as you'll see any gas viscosity become. Now, if we want densities of the gas in oil phases, you don't get those from tables. Those have to be calculated, and they're calculated by using the Blackwell PVT properties that are pressure dependent, little rs and BG for the gas, and big RS and BO for the oil. But together with that, you have to have the surface pseudocomponent densities of the surface gas and the surface oil. And these numbers here will be the same numbers used for both reservoir gas phase and reservoir oil phase. And those numbers will be constant. They'll be required to be input into your software that's using a Blackwell table. When you do that calculation, now I've just calculated the saturated phase densities of this volatile oil system. This is the original density of that at its bubble point, 6,400 pounds. This is the incipient gas density here at 6,400 pounds. And what you see is that the gas densities can be calculated as a function of pressure using this equation. Okay, so now in reality, the surface densities are not constant, because if you looked at the actual calculation of surface density from these changing gases and oils as you deplete down below the initial saturation pressure, you'd find that the surface gas coming from the gas phase is not the same density as the surface gas coming out of the oil phase. And even more different will be the surface oil coming out of the oil phase. It might be 42 API volatile oil, and the surface oil coming out of the gas phase here might be 52 API. So you can have very different surface oil densities here. But the model itself requires these to be constant. So you need to figure out what values to use. And that's an issue that we can talk about in the question session. So basically, that's the first session, the first hour I wanted to go through of material, and the second session we'll look at some more advanced complex issues on the Blackwell properties.